Hello everyone and welcome back to another live stream video where I'm going to be going through a paper. Actually this paper has an open source implementation called QC GitHub. So the author what I want to do is essentially go through this paper and have a better understanding of how this queue chunking actually works. So the paper is here, and let me make my face a bit smaller. Okay. And I'm going to pull out my iPad because I think writing down the equations is really helpful. At the same time, I'm going to start recording on this little microphone I got. So the thing is, it always, this is the right orientation. Now it's starting to record. Okay. All right, and let me plug in my iPad. Like this. Then if we switch over to the scene, then we can see my iPad. Perfect. All right, and let's go to these equations. And all right, so the basic idea, just as a refresher on what Q-learning is, right? So in reinforcement learning, we have the concept of these value functions. So these there's two sort of like value functions. There's the this is the state value representation, and this is the value state representation, and then this is the state action value representation. This is the state value representation. This is the state value representation, and this is the state action value representation. So Q value function. State value and action value. Yeah. Based on my notes, yeah. State value and action value. So, okay. So again, I'm going to repeat this. So in reinforcement learning, we have this concept of a value function. We actually have two different kinds of value functions. One is just the state value representation. So we give you a state and it quantifies the value. And we have an action value representation, which takes both a state and an action. Because in reinforcement learning, generally what happens is you start from a state, let's call it S. You're going to take some action, and you're going to end up in a new state, let's call it S prime, and you're going to get some reward from executing that state in action after ending in this new state. So it's actually more SAR S prime. So this is sort of one transition. The value function sort of tries to capture your expected your return. Return is often referred to as G, and this is equal to the sum of discounted reward times R, something like that. G of T is equal to, so V of S is equal to the E G of T. What's the notation here? The expected return, right? So that's what I was writing. And g of return given st equals s. And the return is equal to the expected value return is equal to the sum of discounted rewards. So this is equal to sum of gamma t if you have rewards where g of t is the sum of expected rewards. G of t is equal to r of t plus t versus t plus 1. There's often this like confusion in notation. Like if you look at our value function, more specifically Bellman equation. Yeah, that's why we often don't write. I see how I just write r as opposed to r prime. Bellman equation. Yeah, okay. All right, let me try explaining this a third time, which should be the best. One sec, what is this? Okay. All right, let me try to explain this the third time. So in reinforcement learning, we have the concept of a value function and a state value function. Sorry. In reinforcement learning, we have the concept of the value function. The value function captures how good a given state is. And we actually have two types of value functions. We have one called the state value function. So this is a function that takes in a state and it will tell you how good that state is. And we have an action value function, which in addition to the state will also take an action. So it'll tell you at this state, if you were to take this action, how good is that particular decision? And as I said, these states capture how good these functions capture how good a particular state or state action is. So how does it do that? Or how do we formalize that? So it is simply equal to the expected return, where return is given by g of t. What is return? Return is simply the sum of discounted rewards. That is, so to formalize, we are at a state. We can take some action, and we're going to end up. Our environment is going to give us some reward, and we're going to end up in a new state. So there's like this famous loop agent, environment, agent. There's like famous diagram, right? So the agent takes some action in some state, and the environment will give you a reward and a new state, right? And then you sort of have this cyclical. This sort of repeats itself, right? It is a sequential decision-making process. So the return here is simply once you step to the environment a lot of times, right? Starting from time step t, you're going to get some reward, and here the t. Some texts, a lot of texts will do r of t plus 1, right? So in this case, let's call it g, right? So in this case, you expect to return at G would be simply your sum of, if you were to sample from your policy, like okay, let's just write G is equal to R plus gamma R at T, like your next word. So this is where I guess notation would be helpful, right? Like a time step T, RT plus 1. Yeah, I think a better notation, I guess, would be, you end up in this, you get the word at time step T plus 1 and state T plus 1. And the expected return should be G of T, and this is given by the reward of T plus 1 plus gamma T plus 2 plus gamma to the power of 1 T plus, 2 T plus 3, etc. Or this is just simply equal to R to the sum of K equals 0, infinity, gamma to the K, R to the T plus K plus 1. That's the definition of return. So a value function is simply capturing the expected return, and same for QSA is also the expected return, but given that your state, given that your starting state given that your state like this is starting from state and after breaking action A, right? Whereas this is simply condition or given st equals s. And if you were to expand this out, v of s by definition, and then this is like the, if we take this return and we write this as a Bellman update, right? So this is equal to r plus gamma v of s t s prime, and this is equal to r plus how do you end up in s prime, right? So this is given by some policy. So you're going to, one is you're going to sample some action, sample from your policy, and then your s prime are sampled from your environment, and that's P S A. Yeah. Yeah, I guess that's I'm just like explaining how reinforcement learning works right now, right? And all right, so our value function captures our value function should capture our expected return, right? So expected return is equal to E of G, right? Where G is simply the sum of discounted rewards, right? That is, your agent steps through this environment, is going to take some state, given some state, and it's going to decide to make an action, and then the environment will give you back a new state and a new reward, right? And then you do this process over and over again. So if you were to take all of these rewards that you accumulate, right, and discount them, that your value function should be able to capture all of that, right? And so this can be written as E of G, where this is like R so a better way to write this, I guess, is V of S of T is equal to E of GT is equal to RT 1 plus gamma RT 2 plus R gamma 2 RT plus 3, right? And this is a very long form, right? And how do we get RT plus 2? You get a reward after you step through your policy and then sample from the environment, right? So a more concise way to write this, more commonly people will write this as some sort of Bellman equation where we sort of like use the same variable, the same value function, right? Because essentially you can notice this is essentially V of ST plus 1, right? And so you can sort of like end up in this form. Yeah, I don't know how to explain this better. I mean, this is pretty obvious. You end up in a new state. How do we capture? All right, so this is just equal to return is, well, first you need some reward, so you need to take some action sample from policy, right? And then you have your state and new reward, award and new state sample from your environment. So this is, once you have these two variables, then you take your R, right? So that's equal to R plus gamma of, okay, now you're in S prime. You need to sample A prime from pi S prime, right? And then you have R prime S prime prime sampled from P S A. And so that's why we use the T notation. Okay. Yeah, I need to think really hard about how to explain these concepts. And what's the most like intuitive way to understand this? The value function captures how much information or like how useful a particular state is in terms of how much reward. The value function captures the expected return of a particular state, where the expected return, more formally, it is called the expected return. Okay. Oh man, explaining this is so hard. Okay. Okay. I think I know how to explain this better. So we're going to start from ST. All right. Mark this segment as the beginning of the actual good explanation. This took like 3 or 4 attempts to get right. And by the end of my explanation, we're going to understand the Bellman update. And that's going to take me around maybe 5 minutes, okay? So in reinforcement learning, right, we have this basic setup of an agent and the environment. And the agent will, think of the agent as the thing that will make decisions. And the environment will be, this is environment. The agent will be stepping to the environment, by choosing actions, and the environment will tell it, okay, you made this particular decision, now you're going to end up in a new state. For example, if imagine you're walking, right? So I'm in this position, I'm in position 1. I'm at, like you can imagine a person is standing somewhere, right? And his decision is to take one step forward. And the environment will tell it, okay, now you are in this new position, right? And so this process goes on and on. So the agent is in some state, and it can decide to take a new action. And then the environment will tell it, okay, now you end up in this new state, but I'm also going to give you some reward. This is sort of like the basic setup of RL. So you have a state, an action, and you end up in a new state and a new reward. So this is sort of the transition, right? And now we can introduce the concept of value functions. Well, what is actually the premise of RL, right? Markov sort of like okay. So we are trying to understand reinforcement learning in the concept. All right, so we are trying to understand reinforcement learning in the context of this value. All right, so today we're reading the Q chunking paper, and before we dive into the intricacies of this Q function, let's just get a refresher on how reinforcement learning works, what are Q functions, and how this all ties together, right? So as a reminder, in reinforcement learning, reinforcement learning is formalized as a Markov decision process. What that means is you generally have some agent interacting with the environment, and the agent can make decisions. So you have states, actions, and rewards, and transition processes and transitions, right? So the agent, given some state, it can make some action, step through the environment, and end up in a new state and sample some reward from it. And that is the basic setup of a Markov decision process. Right, so there are many things we can formalize as a Markov decision process. Let's imagine a human takes one step forward. The environment will tell it, okay, now you've moved one step forward, right? And the action would be the act of taking one step forward. The state would be, you can represent it as like, XY coordinates or XYZ coordinates. Like you imagine like most things can be formalized as a Markov decision process, whether it's games or like chess. When you're playing chess, the state would be the positions of your chess pieces, and the action would be how you decide to move a piece. It could be a human, where the state would be, what is the joint configuration of the joint configurations, and the action would be. Oh, I'm so bad at explaining this, man. How do I teach like Karpathy? Alright. One more attempt at teaching this. It's only gonna get better. So we're reading this Q chunking paper, and we need to understand how reinforcement learning works first. And reinforcement learning is generally formulated as an agent. Like, do we even need to go into that? Like, I probably don't need to explain Markov process, right? So in reinforcement learning, there's this concept of value functions, and there's actually two kinds of value functions. This is the pure state value function, and there's actually an action value function. And both of these represent how good a particular state is. And so how do we capture how good a particular state is? Well, we simply look at the reward that the state would give us, right? So as a reminder, the sort of transitions that, so in reinforcement learning, we start from a state, we can make an action, and we'll end up in a new state, and we actually get a reward from it, right? And so the value function sort of like captures, if you were to, to follow some policy, right? You get into a new state, you get a reward, and continue repeating this process. What is sort of like the expected return? So actually, the formal way to write this is, let's say we are v of st. This is equal to expected return, right? Where return is simply equal to the sum of discounted rewards. So you get reward at t plus 1 plus some discount factor plus rt plus 2 plus discount factor rt plus 3, right? So let's run through an example. If we were to expand this out, right? So you just use s and s prime, but in a multi-step setting, I don't want to just write s prime, so I'm just going to use st, right? So let's say we're in state t, and we just have to pick some action at a time step t. We're going to end up in a new state st plus 1, and get this reward at t plus 1, right? And once we're in the state, the next time our agent decides, or our policy decides to, this action, by the way, is sampled from the policy, right? So the policy is the thing that will tell you, given the state, how do you want to act. And I'm actually going to write some more notation right below, but just bear with me for a second, right? We are at state t plus 1, and then we're going to take a new action t plus 1, and we're going to end up in st plus 2 or t plus 2, right? And then ... So if you were to take these rewards, right, and you sum them up using this discount factor until infinity, or until the end of the episode, that is essentially what this value function captures. But in reinforcement learning, right, so if you were to just like estimate it this way, this is actually called like a Monte Carlo estimate. But oftentimes what we do is just bootstrapping, and this is using the Bellman update. So what you will notice is that this part could actually be replaced by v of st plus 1, right? And this leads us to sort of like the Bellman equation. And the Bellman equation is written as v of s equals the expected value of r plus v of s prime, right? So here I'm going to use, instead of t and t plus 1, I'm just going to use s and s prime. And so here I'm going to use the notation. So right now we're at a state s, right? So we need to get an action. How do we get an action? We sample from the policy, right? So if you're not familiar with this notation, this just tells us the probability of this action. It just like sampled from S, right? So imagine this is some action sample from the probability distribution of this policy, right? So let's say our policy could say, let's say we have 2 discrete actions, and each action has a probability like 33%, and I sample from it. So one of them will be chosen. That's our action, and then to get our new state and our reward, or it should be our reward, we get a reward and then we end up in a new state, that is going to be sampled from our environment, and we'll just use P as the notation. And so that's essentially how we get this Bellman update, right? And so here, like, this works for one update. That's why like the sampling is kind of weird. It would be like very long. But it's essentially this, right? This is like how in practice it looks. And so if you write this out, you can actually expand this. So if you want to have the full equation, I think this is like the sum of a probability pi a given s, sum r s prime pi. You just expand this out, right? It's sum of probabilities. That's how you get the expected value. So that's our value function, and the if you're looking at our QSA, the action value is very similar, but instead of r plus v s prime, we now have the expected value of r plus, and I forgot a discount factor here. Alpha q q s prime a prime plus, and this is alpha sum of actions. I think it's that, right? Actually, value function, I'm not sure. I'm not sure about the Q value function. Yeah. There's another expectation here. Okay. All right, so we understand the concept of value functions. And see, all of this is just terminology. A value function captures, I guess, how good a particular state and optionally a particular action, if we're talking about the actual, if we're talking about the Q function. Why the Q function is useful is because if we just have a value function, it doesn't tell us sort of what is the most optimal action, right? So if you have a Q function and you already know all the values, and there's discrete actions, you just know your optimal action is just going to be the argmax of Q, right? So that's Q learning, and then that's the basic idea of Q learning is you want to train a Q function that is able to capture, obviously, that is able to capture sort of what your policy, like the actual true values of these states and actions, given some fixed policy, right? But that's the difficulty of Q learning, is it will take time to converge, but there's some proofs that it can converge, right? And that's how we're able to get like a lot of the advances with deep Q learning. But this paper introduces action chunking, and so action chunking is essentially this idea like, so if you look at here, right, our action is generally, it's just one step action, but you might want more recently with the action chunking of transformers paper, there's been the concept of action chunks. So an action chunk is like equal to AT, and here like they bolden it, AT plus 1 T plus H minus 1, I guess, if that's the horizon. H equals horizon. Yeah. And so how do we do reinforcement learning? Because our policy, when you sample you can't just sample a single action from policy. You actually have to sample an action chunk. So sort of like, how do we integrate this with our reinforcement learning framework? And I guess this paper shows like how the naive way to do it and the real way to do it doesn't really work, right? Because what you can imagine is you have a bunch of actions, and if you still do this update, it is biased. So, okay, I actually did not go through that part, and I need to go through that part right now. Actually, I did go through it, but I didn't fully understand it, right? So this is what I was explaining to you guys. Gamma, this is the one-step return. This is the n-step return, where if you just do this, it's biased. Oh, okay. I'm also like hella tired, guys. I need to go to sleep, actually. Oh, man. Just got really tired. Okay. Alright. If I'm tired, I'm going to sleep and nothing else. Alright, I need to dry my clothes and then I'm going to sleep. Okay. Alright. Didn't get very far, but yeah, I think at least like these equations I need to be engraved in my head. Alright. I'll see you tomorrow morning. I'm gonna do a much longer live stream tomorrow morning.